Here is another type of example involving integration by parts. We're asked to use integration by parts to find the integral of e to the x times cos x. For reference, we have the integration by parts formula at the top of the screen. However, you should try to learn this formula by heart. So, our first job is to choose which factor in the integrand will be u and which will be v dash. As in the previous videos, we need to make this choice in such a way that the integral on the right hand side of the by parts equation becomes something we can solve. But upon inspection, we see that in this case it doesn't really make any difference. E to the x will stay the same whether we integrate or differentiate it, and cos x will become either plus or minus sin x. So let's choose u1 is equal to e to the x and v1 dash is equal to cos x. It'll become clear in a little while why we've chosen to add a subscript 1 to each of these. In the meantime, u1 dash is equal to e to the x and v1 is equal to sin x. Now, we put this into the formula to get that the integral of e to the x cos x is equal to u1 v1, which is e to the x sin x, minus the integral of u1 dash times v1, which is e to the x sin x. Now, let's take a look at this integral on the right hand side. In the last two videos, this technique worked well because this integral was something we could compute. Now, however, it's still a product of two functions, and in fact looks very similar to the integral we started with. In this case, the best way to proceed is to do integration by parts a second time on this integral on the right. To show you why this works, we'll just do it on our example. So we're now going to choose u2 is equal to e to the x and v2 dash is equal to sin x. So u2 dash is equal to e to the x and v2 is equal to negative cos x. Again, using the formula, we have that the original integral is equal to e to the x sin x, that part hasn't changed, minus, well, now we'll compute this integral on the right hand side using the by parts method. So we have u2 v2, which is negative e to the x cos x, minus the integral of u2 dash times v2, which is e to the x times negative cos x. Now, we have the original integral is e to the x sin x plus e to the x cos x minus, because we have three negative signs, the integral of e to the x cos x dx. We notice that the integral we now have on the right is the same as the original integral. So, if we let I equal the integral of e to the x cos x, then we have that I is equal to e to the x times sin x, plus e to the x times cos x minus I, which implies that 2i is equal to e to the x times sin x plus e to the x times cos x. So that I, which is equal to our original integral, i.e. the integral of e to the x times cos x dx, is equal to e to the x over 2 times sin x plus cos x, plus some constant of integration, c, which we should put in. So you see, and indeed it is often the case, that when you are integrating the product of an exponential function and a trigonometric function, you have to perform integration by parts multiple times, often twice, but sometimes more, until you have an integral on the right hand side that is the same as your original integral. At this point, you can rearrange the equation to solve for your original integral.
I, and his happiness was one with hers.